Swayam Prabha. Digital India. Educated India.
Hello and welcome everyone to this course on gas turbines and jet engines. So, today is lecture 11 of this course. So, this is the first lecture of week 3 and today we are going to learn gas turbines with intercooling and regeneration. So, both intercooling and regeneration are present together. Okay. So, concepts which are going to be covered. So, we are going to analyze Brayton cycle, okay, which we know already is the basic gas turbine cycle. Okay. So, Brayton cycle when it is combined with intercooling as well as with regeneration, okay. And we are going to see that this is a very powerful combination and this can lead to significantly high efficiency of the cycle, as well as because of adding intercooling to regeneration, the scope for regeneration increases also quite significantly. Okay. Okay, so, before we go into the discussion of today's topic, let me quickly just revisit what we have discussed in the previous two classes. We had started with the process called intercooling. So, what was the process? So, intercooling is a process where the compression in the compressor is divided into multiple parts. So, we have seen compression divided into two parts and in between there is a heat removal process which occurs through a heat exchanger. This heat removal process is known as intercooling, okay. Because it occurs between two compression processes. So, that is why this name is given, and while so, once the compression is done in the low pressure compressor, the air is passed to the intercooler where it is cooled by circulation of cold water, and then again the cooled air is passed to the second compressor, and the rest of the cycle is continued as usual. Okay. Now, one of the things that we have seen in intercooling, for example, if I draw the intercool cycle on the right side. So, I will draw the TS diagram of the intercooled cycle. So, let us say that process 1 to 2 is the low pressure compression. There is some issue. Okay. So, then 2 to 3 is the constant pressure heat removal or intercooling process, and 3 to 4 is the high pressure compression. Okay. This we already know, and we close this cycle with the other processes. 4 to 5 is the conversion, 5 to 6 is the expansion. Here we are considering a single turbine, and then 6 to 1 is the constant pressure heat removal, which is added to close the cycle. Okay. So, now what we have seen is that if we had no intercooler, okay, if we had not used any intercooling, then for the same design parameters the outlet temperature would have been much higher from the compressor. Compressor outlet temperature would have been much higher. So, it would have been 4 dash, but because of addition of intercooler, the compressor outlet temperature is considerably lower. Okay. So, this means that the difference of temperature between this compressor outlet temperature and the turbine exhaust temperature is considerably increased. Okay. So, it is considerably increased when intercooler is added. As you can see in this example, without the intercooler there was no positive difference at all, and now you have significant difference, which means that when intercooler is added, the scope for achieving regeneration is considerably enhanced. Okay. So, we get much higher effect by adding a regenerator. So, with this idea the regenerative intercooled cycle is designed. Okay. So, let us take a look at how the intercooled cycle works. So, you have the first compression process going from 1 to 2. So, this is the low pressure compression. So, we will draw the cycle parallelly. So, it will be similar to our intercooled cycle, but with the regeneration also added. So, this is the 1 to 2 is the low pressure compression. So, starts from 1 goes out at 2, and then you have the intercooling. So, cooling of the air going from 2 to 3 in the heat exchanger, which is known as intercooler as previously discussed, and then 3 to 4 we have the second compression process, okay, in the second compressor. So, this is the high pressure compressor, this is the low pressure compressor. Now, after that at 4 the exhaust gases, not exhaust gases, means the outlet air from the compressor is passed to the regenerator, where it gets heated by the regeneration process. Okay. So, we will draw the regeneration later on. Let us say that this is. So, we will go as per this diagram. So, this will be after compression, this is state 6. This is 7. Okay, so now the regeneration process, in ideal regeneration where the effectiveness is 1, it will go from 4 to 5. So, this will be the regeneration process 4 to 5, and then on the gas side or the conversion product side, we have the regeneration again for the ideal case where the mass flow rate is considered to be same. The conversion products go from 7 to 8, where 8 is at state temperature, not state temperature T2 itself. Okay, so, T8 is equal to T2. So, this completes the cycle. So, from 8 to 1 the cycle is completed by adding constant pressure heat removal process that we have done for all the other cycles. So, considering optimal conditions for the intercooler, we know that T4 should be equal to T1, sorry T4 should be equal to T2, which is also equal to T8, okay, if we consider that in regenerator effectiveness is 1. Okay. So, optimal condition. And then similarly, we know that T1 is equal to T3. So, T3 equal to T1, which is based on the ambient condition. And for 100% effectiveness of the regenerator, we have T5 equal to T7 or T7 equal to T5. Okay. So, the actual heating in the combustion chamber now goes from 5 to 6 instead of from 4 to 6. So, we can see that the heating is from external source is considerably reduced, whereas the work output remains same. work output is from 6 to 7 is the turbine work output, and compressor work input is going from 1 to 2 and from 3 to 4. Okay. So, work output remains same, the heat addition is considerably decreased, which means that we should get a much higher efficiency from the cycle. Okay. So, again if you compare to the simple intercooled Brayton cycle, the effect of regeneration is very strong, and intercooling is generally always used with regeneration. So, that we can have this combined benefit, and this occurs because the inlet temperature to the regenerator is significantly lowered if we use a intercooler, and as a result we get considerable range of temperature for the regeneration to occur. Okay. So, let us analyze this intercooled cycle with regeneration further. By the way, if we also, you should also be able to draw PV diagrams of these cycles. So, although I have not drawn for most of the cycles, but I have left them as exercise to the students. But let us say that, let us draw it for one case, okay, just to explain how the PV diagrams look like. So, we have the TS diagram and we will draw the corresponding PV diagram. TS diagram we will draw quickly. So, going from 1 to 2, sorry, this is 1, 2, 3, 4, then 5, then the conversion process going from 5 to 6, 6 to 7 expansion in the turbine, and 7 to 8 is the regenerator on the gas side, where the heat transfer occurs from these conversion products. Okay. So, the corresponding PV diagram also is simple to draw, and you should consider each of the processes and draw accordingly. So, 1 to 2 is an isentropic process. So, isentropic compression, which means that the volume will get reduced in the PV diagram and pressure is increased. Okay. So, it goes from 1 to 2 like this. Then a constant pressure heat removal in the intercooler. So, the pressure remains constant. So, line is horizontal, because we are removing heat at constant pressure, temperature and specific volume will go down. So, we go in this direction, this is 2 to 3, and then again another isentropic compression process, we go from 3 to 4. Okay. So, these are the two compression processes, this is the intercooling. Then we have constant pressure heat addition, pressure remains same, but because considerable amount of heat is added, the temperature increases and correspondingly the pressure also increases. Okay. And not the pressure, sorry, the specific volume also increases. Pressure of course remains constant, as the process itself says. So, then we will have the heat the expansion in the turbine. Okay. This we are calling as 6, this is 7, and then we have not yet drawn the regeneration processes. So, if I draw by using another color. So, the regeneration here was constant pressure heat addition, okay, and that occurs by heat exchange from the other side, constant pressure heat removal. So, here going from 4 to 5 is the constant pressure heat addition, and then 5 to 6 is the conversion process, and on the other side going from 7 to 8 is the constant pressure heat removal in the regenerator, and then from 8 to 1 is the heat removal to the external reservoir, which this process we have added to complete the cycle. Okay. So, now the net work output from this cycle, we already know that this should be equal to W T minus W C 1, first compressor work output minus second compressor work output. This we can write in terms of the C P and delta T values, right. So, C P into T 6 minus T 7 minus C P into T 2 minus T 1 minus C P into T 4 minus T 3. This is the net work output. So, non-dimensional net specific work output in that case will be W net by C P T 1, where C P will get cancelled and we are left with T 6 by T 1 minus T 7 by T 1 minus T 2 by T 1 plus 1 minus T 4 by T 1 plus T 3 by T 1. Okay. Exactly similar to the intercooled cycle without regeneration. Okay. I am rewriting this because so that we can revisit what was the derived expression for the previous case also, and we can know that same expression is valid in this case also. So, what is T 6 by T 1? T 6 by T 1. Okay. T 6 by T 1. So, this is for the expansion in the turbine. We know that for expansion in the turbine. So, we have the overall pressure ratio is R and is P 6 by P 7, and the compressor pressure ratios we had defined as R A to be P 2 by P 1 and R B to be equal to P 4 by P 3, and we had seen that R should be equal to R A into R B, and at optimal condition we know that optimal condition is achieved when R A equal to R B equal to root R, and correspondingly we had defined the value C. C is R to the power gamma minus 1 by gamma, which is equal to C A into C B, and for optimal condition again C A is equal to C B equal to root C. Okay. So, T 6 by T 7 sorry T 6 by T 1. So, this by this is the maximum temperature ratio. So, this is equal to T as per our definition minus T 7 by T 1. T 7 by T 1 we can write as T 6 by T 1. Okay. So, I will write on this side. This can be written as T 6 by T 1 into T 7 by T 6, including the turbine process. So, T 6 by T 1 is equal to T and T 7 by T 6 is equal to 1 by R to the power gamma minus 1 by gamma, which is 1 by C. So, this is minus T by C minus T 2 by T 1. So, for the first compressor, so this is R A to the power gamma minus 1 by gamma. So, this is C A. Okay. In this case, we will assume that this is already at optimal condition. So, this is equal to root C, okay, and then plus 1 minus T 4. So, T 4 is equal to T 2 in optimal condition. So, T 2 by T 1 is again root C plus T 3 by T 1. So, T 3 is equal to T 1, we have discussed this. So, this is equal to 1. So, this is equal to T minus T by C minus 2 root C plus 2. Okay. So, this is the expression for net specific work output in non-dimensional form for the optimal case, where we have the maximum efficiency, a maximum work output. Okay. So, this is the maximum work output, and that is what we are going to consider for these cases. So, this is not changed, but the efficiency is going to be changed. So, what is the value of efficiency? Efficiency we know that. So, as per the standard definition, this is the net work output. By the way, when we say efficiency in all these cycles, we mean that these are the thermal efficiencies, okay, first law efficiencies of the cycle. So, W net by Q in, and what is Q in this case? Cp T6 minus T7. So, W net itself is Cp T1 multiplied by what we have derived in the previous slide, T minus T by C minus 2 root C plus 2, and Q in we can write again by taking out this T1. So, Cp T1, okay, remember what is it? T6 minus T5, T6 minus T5. So, T6 by T1 minus T5 by T1. What is T6 by T1? We have already seen previously, this is the temperature ratio T, okay, and so this gets cancelled. So, this is equal to T, and what is T5 by T1? So, for the optimal case, T5 is equal to T7. So, this is same as T7 by T1, and T7 by T1 also we have seen is equal to T by C. Okay. So, this is equal to T by C. So, which means that the efficiency can be expressed as T minus T by C minus 2 root C plus 2 by T minus T by C. Okay. Or we can write in a slightly different form. So, this is equal to 1 minus 2 root C minus 2 by T minus T by C. So, this is the efficiency in terms of the pressure ratio, which is embedded in this C. So, C is the is pressure ratio to the power gamma minus 1 by gamma. So, in terms of pressure ratio and the temperature ratio, like for all the cases we have already derived. So, this is a different expression, and without plotting this, it is difficult to say what is the exact variation with respect to C and T, but qualitatively we will plot here, and later quantitative plot also I will show by preparing drawings using some numerical tool for plotting, and there you can see exactly what are the values which are involved in the characteristic curve. Okay. So, now if we want to draw the performance characteristics, okay, we will draw the performance characteristics. So, we need to only draw the performance characteristic of efficiency versus R, because the net work output versus R characteristics are exactly same as the previous case, which was for the pure intercooled Brayton cycle without any regeneration, because there is no change in the work output, there is no change in the characteristics there. Okay. But the efficiency of course changes, because now we have reduced the heat transfer, we expect that efficiency is going to be significantly higher. And we also know that when regeneration is added to a system or to a cycle, the behavior of the efficiency curve changes completely and the efficiency behaves in a different way, where it decreases with increasing R. Okay. So, anyway, so this is R equal to 1, which is the minimum theoretical value of pressure ratio. So, now we will draw some reference curves. So, reference, of course, every time we should have the standard Brayton cycle efficiency. Okay. And if you remember, for the intercooled cycle, the efficiency curves are lower than the standard Brayton cycle curve, but they approach the standard Brayton cycle curve if we keep on increasing the value of t. Okay, so, with increasing t, the efficiency improves, and let us say starting from t equal to, let us say this is t equal to 3, t equal to 4 and t equal to 5. Okay, similarly, we can have t equal to 6 also. So, the efficiency keeps on improving and the nature of the curve is same as the standard Brayton cycle, but the efficiency is always less than the standard Brayton cycle efficiency. So, now for this intercooled cycle, intercooled plus regeneration, okay, what is the limiting value at R equal to 1? At R equal to 1, C is also equal to 1. So, this goes to 0, 2 minus 2, okay, goes to 0. So, this becomes, and this also t minus t also goes to 0. So, directly from here you cannot say without taking the limit. Okay. So, now we will use another color. Let us say we will use this. So, again similar to pure regeneration cycle, the efficiency decreases and at some point there is crossover with the corresponding intercooled cycle efficiency curve. Okay. Let us write it in a better way. T equal to 5, similarly we will have t equal to 4 and t equal to 3. Exact nature we will see by plotting the numerical values by using something which is known as design point calculation, which we are already doing, but we have not yet used that name. Okay. So, these are the intercooled plus regeneration curves, and nature is similar to normal regeneration, but because intercooling and regeneration together is very effective, the efficiency actually increases compared to simple regeneration cycle. Okay. So, if for simple regeneration cycle, if we have efficiency similar to this, t equal to 5, t equal to 4, t equal to. So, the actual efficiency here for the combined intercooled and regeneration cycle is higher than that of the pure regeneration cycle, which is in contrast with the behavior of adding intercooling to the standard Brayton cycle, where adding intercooling decreases the efficiency. Same thing we have seen also for addition of reheat to regeneration. So, in this case by adding intercooling to regeneration, the efficiency actually increases, because so what was the reason for this? We had already discussed, because adding intercooling increases the range of temperature significantly for regeneration, so that we can have a much more effective regeneration process, or much more much larger regeneration over a larger temperature range, which reduces the fuel in requirement by significant margin. Okay. So, to summarize, efficiency can be significantly improved by combining regeneration and intercooling. So, this is a very effective combination, and later we will see that this is better than even reheat plus regeneration. So, you get very near to the highest efficiencies which are possible among all these different cycles, and the efficiencies are high. See, for all, like all regeneration cycle, efficiencies are high at lower values of R and at higher temperatures. So, the with temperature ratio the efficiency increases, which is understandable, because if the temperature increases, maximum temperature, you get a larger range for regeneration and more work output also from the turbine. And lower value of R, what was the reason? Lower value of R means that less compression, which means again that the scope for regeneration is higher. So, that is why the behavior is completely different as compared to the cycles without regeneration. And the net work output loss remains exactly same as those of pure intercooled cycle. So, we are not going to draw them again. You can refer back to that, which was discussed in the previous classes. So, we can conclude today's lecture. So, what we have done is we have analyzed Brayton cycle with intercooling and regeneration. This is a very important cycle for industrial gas turbines, because this can give very good performance characteristics. We have also learned the performance characteristics of intercooled regenerative cycle and seen how they compare with other important cycles. Okay. So, these are the references. The image, one of the images on the slide was taken from the book by El Sayed Ahmed, and other books are for the reference for the background study. Okay. So, with this we conclude today's class, and we will meet in the next class again. Thank you.